Good morning and welcome to we couldn't agree about it Wednesday. I think it's a pretty wonderful Wednesday. People aren't on the same page yet, but we'll get there, hopefully. In any case, today we have one new topic, and that is to look at situations like this. So I would invite you on your handout, this is on the back side of your handout, is to create a triangle with these conditions where we have an angle A. And remember, the way we always label these triangles is if I know that I have an angle A, that's going to be opposed to this side A. So here we go. Here is some angle, 26 degrees. And that actually looks a little bit past 30 degrees, what I just drew. Maybe not. Maybe it is pretty close to 26 degrees. And I know this opposing side here is 7 degrees, and one of these sides is B. So when we have a triangle, we're going to have things like A, B, C, and then this would be side A, this would be side B, and this would be side C. The associated side is the one that the angle opens up. So between my fingers is the side that's being opened up by the angle made by my two palm heels. So if this is angle A, 26 degrees, then this side over here would be, let's say, 7. It might be like that, 7 centimeters. And then this side be B. We'll call this B, 15 centimeters. Okay, so try and find for me the other sides of the triangle, the other angles, and we are going to notice here that that gives us the tools we need to do sine law, that opposed set of side and angle. So what does this triangle look like? Have you drawn it? Can you solve it? Go ahead. So how would I solve it? Well, let's take a look. If we know this side, we know this side, and we know this angle, that already gives us enough to use A over sine A will be equal to B over sine B. And this is angle B here, because it's opposed to this side there. So that's a formula we can use to solve this angle. Once I have that angle, I can also use that to solve this angle, and I can solve this side. I'd solve this angle just by doing 180 degrees, subtracting the other two angles. That will give me the missing angle. And then once I have that, I can set up my C over sine C to find this length of this side. And let's do that. Okay, so let's set up this one here, A over sine A. I'm just going to zoom in so I can get more space to write. You can't do that unless you have a magnifying glass and some way to minimize your work. So here, I know A and I know sine A, so I'm going to put those in. So that's going to be 7 over the sine of 26 degrees. And that's going to be equal to B is 15 over sine B. Sine B is unknown. But I like my unknown on the bottom here because, actually, no, I don't like my unknown on the bottom there. So I'm just going to flip it all. So what I'm going to do is, to solve this one, first I'm going to flip everything. Sine 26 degrees is equal to sine B, sine beta, sorry. And that's over, sine B, sorry, sine B. And then that's over 7. And this was over 15, but let's multiply that by 15. So I'm going to multiply both sides by 15. And that way I can get something that I can calculate sine B with. So the thing that I will punch on my calculator, there will be 15 times sine 26 over 7. And then I get 55.7 when I do that. I want then the inverse sine of 55.7. So I'm going to go shift inverse, and then I just push my, shift inverse of, 55.7. This calculator wants me to do it this way. Huh? There's no such thing. This calculator is annoying. There, multiplied by 15, multiplied by, divided by. There we go. And then I do inverse sine of that. And I get 70 degrees. 70 degrees for beta. So the way I set up my algebra there is to find b, I would take the inverse sine of this. Oops. Jeez, I'm really not doing very well with that today. This here. This is the thing that I will punch in sine inverse. So 15 over 7 multiplied by sine 26 degrees. Now that will give me b is equal to 70 degrees. Okay. So now, have I solved this? Do I know all the things about this triangle that I need to know? This is 70 degrees. Yep. Why not, Rylan? Yeah, I could now get this angle here. So 26 degrees plus 70 degrees gives me 96 degrees for that angle. And then I could use that to find this side. But my calculator just told me that this was 70 degrees. Are there any other angles that have the same sine as 70 degrees? So let's take a look at it with our angles in standard position idea here. So if I have here my xy plane, and I'm going to have an angle 70 degrees, we know that that angle has a sine of opposite over hypotenuse. Is there another angle with the same opposite and the same hypotenuse? Just the negative adjacent? Dave? Sorry? If we reflect it through 90 degrees, if we reflect this over here, this angle here, where I just reflect this point to there, this is the same reference angle, 70 degrees, and that would give us another angle with exactly the same sine. Yeah, it's reflected over the y-axis. If we reflected it over the x-axis, that would give us a negative opposite. So that would be the negative sine. You see? So what is this angle that has a reference angle of 70 degrees, but it's in the second quadrant? Dave? 110 degrees. So the angle 70 degrees or 110 degrees all have the same sine. Punch that on your calculator. Sine 110 is 0.939, and then do sine 70 is 0.939. It's the same. It's exactly the same. So which one of these is it? Could this be 70 degrees or could this be 110 degrees? Well, we can have obtuse angles inside triangles, so long as they're less than 180. Yeah. Oh. So let me get a fresh one here, fresh space. So yeah, it depends on how it's drawn. That's exactly right, Riley. We talked about a triangle here, and I'm going to draw two different triangles. Here is 15. That was our B. And then we had a 7 that was like this. And this was an angle 26 degrees. Okay? This was 26 degrees. Now, we could say this is about 70 degrees here, and that would look about right. This is a little bit less than 90, and that works. But we could have also drawn the triangle in this way, 15, and this is still 26 degrees here, and this is still 7 here, but now this is 110 degrees. Both triangles are possible given the initial conditions we set. And this is called the ambiguous case of the sine law. It is ambiguous from the information given whether we have that triangle or this triangle here. These are still both 7 degrees, but this is 110 degrees here, and this is 70 degrees here. I like to notice that there's a kind of elegance with how the math works for both triangles, and yet we don't have a solution. We need to now add more information to the question to clear up that ambiguity. Is it an obtuse triangle, or is it an acute triangle, or just a scaling triangle, acute triangle? Okay, so let's carry on. So this is the ambiguous case of the sine law, where we need to be a little bit more like a detective to solve these questions. So we have two different triangles here, and here's an example of what that might look like. We have this A is the same length, and yeah, it's but it could be created by the same angle here in both cases. So when we have these types of situations, sometimes it helps to look at the algebra to know what kind of situation we have. If we take a look at b sine A over A equals 1, then that's a right triangle. That has to be a right triangle. If we have this angle here, and this comes out of our sine law, we'll recognize sine A over A is equal to sine B over B. And this would be capital B. If we rearrange this such that B sine A over A equals sine B, and if this equals 1, then we have a right angle triangle. And why is that? Well, sine B must be 1. So let's draw this triangle. Here we have side B. Here we have the angle A. This would be angle B. And here is side A. If I rearrange sine law and get a 1 here, well, just do inverse 1, sine inverse on your calculator. That tells me it's 90. So sine of 90 degrees is 1. And why is that? We can see that here. When I rotate this angle such that the hypotenuse is the y value. That's the case where the x value is 0 and the y value is the same as the hypotenuse. That's opposite over hypotenuse is sine, but the opposite is the hypotenuse. And that only happens at 90 degrees here. Then sine is 1. So that's how you know that this is giving you a right angle triangle. There's only one way to make that triangle work. This you can think of this angle, this line here, as if it swings in either direction. If I swing it out that way, it's not going to hit this bottom line C. It's not going to hit this C. It's like a pendulum that only touches C down here at 90 degrees, and then it goes up again. So there's only one solution. Similar to finding a value for a quadratic or a quadratic with a single root. There's no plus or minus to it. If we have a different situation where b sine A over A is less than 1, now that's a rearrangement of my sine law, which is sine A over the side length A equals sine B over B, but then I multiply both sides by B. Okay? So these cancel, they go away. And this is saying if you find that sine B is less than 1, we're either going to have 1 or 2 triangles. And why is that? Because there's 2 different ways to get a sine value that's less than 1 because of this property of sine. The cast rule states that sine is going to be positive. Here is cast, C-A-S-T. all the trigonometric ratios are positive here, so we'll get positive values of sine that are less than 1 or bigger than 0 in here. And over here, we also get positive values of sine. We're also able to create triangles here that have angles all the way up to 180 degrees. And they'd be similar to triangles that have angles that are on the opposite side here. So you'll get either an acute or an obtuse angle, and sine law won't tell you which one it is. So you need to take a look from your diagram whether you have an A that's on this side or an A that's sloping out on that side. This would create an obtuse triangle with an obtuse angle here, and this would be an acute triangle with an acute angle and an acute angle there. If A is longer than B, there's still only one way to set it up. But if B is longer than A, you get this thing that's like a pendulum that can swing from point C in this way or this way. And this could be hitting the line C at 2 different points as it swings through this part of a circle here. Because it's hitting at 2 points, it's like having 2 solutions to a quadratic. Similar in that way, you can sort of connect that with that idea. The last situation that you could have is where there is no solution. And that's going to be created when you impose a value on the sine that's bigger than 1. Because sine its maximum value is 1, if you're asking your calculator to do this, like you say, okay, I've rearranged sine A over A equals sine B over B, and then I move this B over here. So this is saying if sine B is bigger than 1, that's a no solution situation. That's where you're asking to create a triangle out of this side length B that's very long, and this side A that's not long enough to ever touch this line C down here. It would just swing like a pendulum above this line. It doesn't create any triangles. So that's a situation where you have no triangles created by that thing. So we can use this idea to quickly find out how many triangles you could draw with these different diagrams. So let's take a look at these different situations and how we'd set that up. Here I would say, well, what's the value of sine A over A equals sine B over B? But I'm going to multiply both sides by B and evaluate this expression and to check for what is the value of sine B. Will it be a situation where it creates 1 triangle, 2 triangles, or no triangles? So let's punch this on our calculator. I am going to punch here B divided by A, so that's 12 divided by 34 equals about 0.35. And then I'm going to multiply that by sine of 30. And sine of 30 we know is exactly a half, and that's equal to 0.176. So that's telling me that in this case sine B is 0.176 because this is between 0 and 1. That's telling me I have some angle that's in here or some angle that's in here. And so that's possible. There's 2 possible solutions. And because B is less than A, there's actually only 1 triangle that can be created here. So this is 1 triangle. Since A is greater than B. Okay? And that's going back to this situation here. 1 triangle when A is greater than B. So this is a 1 triangle type problem. Down here, B is 20 degrees, B is 5, and C is 15. So here we've changed our letters. We don't have A and B anymore, but we apply the same ideas. So there you would take sine B over B, sine big B over B, multiply by C, and find out what is that. That's going to give you the value of sine C that's required to solve this type of problem. So I go 15 divided by 5 equals 3, and then I'm going to multiply that by the sine of 20, and that gives me 1.02. So here I have a number which is greater than 1. So how many triangles can we make here? Dave? Yeah, we can't make any triangles. This is an impossible situation. No triangles. Okay. And then we have one more situation here to take a look at. If m is 50 degrees, n is 12, and m is 10, then we could create this expression, the sine of m over m multiplied by n is equal to, and then you just plug that on your calculator. So 12 divided by 10 is 1.2 multiplied by the sine of 50, and that gives me 0.76. Because this is less than 1, bigger than 0, of course, and here the n is greater than the m, so that will give us how many triangles? Here, we just need to draw a quick diagram here. Here's my 50 degrees. It's not quite 50 degrees, but this is just a diagram. And we have a side 12, and this is side 10. This is now looking like that pendulum that can swing and touch twice. It's shorter than this. It's shorter than the arm that it's being hung by. So it can hit the C line at 2 points. We know that this is 2 triangles. I find using this formula to not be intuitive. It's okay. I don't mind this method. I work best by drawing lots of pictures. So I would encourage you to do the same thing when you get to confronting some of these questions and looking at how many triangles can we create here and what do these triangles look like. So let's take a look at this situation where we have a B angle of 34 degrees, 15 centimeter, and a 20 centimeter side. Okay, so right away I notice that this side B that's opposite this angle is shorter than the arm that it's hanging on. So if sine is less than 1, I know that this will be a swinging side that could hit over there or it could hit over here. So let's take a look at what our picture could look like. We could have this situation. I should draw it a little bit more extremely. So if we had this situation, it might look like this, where this is 20, this is 15, and this is angle 34 degrees. Notice the way I set this up. It just matters that I have my B angle and my opposed side that are related, these two sides, the same letter. So we know that that's implying that they are a set of angle side that are opposite. Could be this situation where this has swung out this way. And it could also swing this way here and make another triangle like that. Something looking roughly about like that with another side 15. So let's take a look at the 2 possible triangles that we could make and the 2 different measures of, actually I'll do this one here, angle C, or for our other triangle, angle C. Okay, angle C is either this angle or that angle, depending on how we create the triangle. So let's calculate the 2 different values of C. That's what we're being asked to do. So here, I know that sine 34 over 15 is equal to the sine of C over 20. By rearranging, we're just going to multiply both sides by 20. So 20 over 15, same thing. I'm not going to punch 20 over 15 on my calculator. I'm going to punch 4 over 3. Sine 34 is equal to sine C. So I know that C is equal to the sine inverse of, and this is all in big brackets here, 3 over 4 sine 34. And that will give me the value of C. But it will give me the first value of C. There will be another possible value of C that we'll find here. And that will be the related, the angle that's related to that angle by the same reference angle, C. So let's calculate that on our calculators. I go 3 over 4 equals multiplied by, whoa, that's not right. 3 divided by 4 equals, yeah, there we go, multiplied by sine 34 equals, okay, so I get 0.41, and now I take the sine inverse of that. So when I do this, I get that that c to the nearest degree is 25 degrees. So c equals 25 degrees. What other angle could that be? And that would be this situation over here. So this c would be 25 degrees. That's the acute angle. What would the obtuse angle that's related to it be? Dave? 25. And then you go 180 minus, yes, 155. So how did you do that, Dave? Yeah, so this would be 180 minus 25. You could think about it here like if this is 25, then that one there 25, so this is 180 minus 25. Or you can think about what Dave probably did was he said, if I have this angle here, it's 25 degrees, then the related angle would be over here, with making another angle with the x-axis there, where you would take 180 and subtract 25 degrees. And like you were saying, Avery, it's probably easiest just to draw a diagram real quick or to start visualizing the diagram in your mind to figure out I need to do 180 minus 25. To find this angle here is 155. So this angle there, 155. So these are ambiguous sine law cases. If you can create applications questions that use ambiguous sine law, that's pretty cool. That's pretty neat. So how will we do that? Well, let's take a look. So I've given you this task of create some interesting problems for us today. Here, let's create another alien abduction problem that would use the ambiguous sine law case. So I am going to put, does anyone want to be in this problem? Peter is over here. So Peter, I'm going to just sketch Peter here. Here he is, and he's wearing a toque. Sorry if it looks like a poop emoji. All right. And then here we go. I think those are your exact proportions. Very good. Okay, this is Peter. And he is going to look up at an angle of 34 degrees. We just worked with 34 degrees. It was pretty cool. And he is looking up, and he uses a rangefinder to notice that this flying saucer here is hovering up there, and he knows this distance to be 233 meters. Okay. Someone else is looking up at a different angle, and they notice that the distance is what? So what would they notice the distance to be here? Well, we could use my favorite number. Let's say they look up at 144 degrees. Sorry, 144 meters. They're looking up. And what we want to know, and so who else, there were a few hands that went up. Who else wants to be in this problem with Peter? Okay, we have Jonah in the problem as well. So here's Jonah. Jonah is here. Jonah is there. And your exact proportions. Okay, there we go. All right, so here's Jonah. All right, and you're looking up at 144 meters. We want to know this distance. How far apart are Peter and Jonah? 3 feet. Yeah. So find for me this distance, x. Or find that maybe they're not on the same level. Like we can't do this problem. It's not there. The pendulum will swing and not work. I know that that's not the case. I know that it will touch. But find out, is there one distance that could be between them? Or could they be two distances apart? Or does this problem not compute? How do we solve this problem? Solve this problem. There's one example of a problem we could create. And And then you could say to someone, solve it. Tell me how far apart Peter and Jonah are. Maybe they're being interviewed by, what's the local newspaper's name? I don't know this. Local newspaper? Like in Barrie, we have Barrie Today. Do you have Collingwood Today? I think it's a chain of newspapers, small town community newspapers, but it's a chain. Is there Collingwood Today? They're being interviewed by Collingwood Today, and they want to know who is closer. We know that Jonah will be closer here, but maybe we want to know what is the distance between the two of them. What is the distance for each of them to this baby that's being abducted here? They want to know very quickly who should run for help and who should try and save the baby. There's the beautiful baby in the bassinet there. Okay, being abducted. What angle does Jonah look up at? These are all things we can solve with sine law. This will be a known triangle once we do it. How high does the baby go? That we can solve as well. Get your pencils moving. Get your calculators moving. Find me these things. Here are the things we want to know. We want to know distance between Peter and Jonah. We want to know how much closer Jonah is than Peter. Okay, so let's make some questions. A, how far apart are they? B, how much closer to the abducted baby is Jonah? If we knew that Peter could run 1/4 faster than Jonah, maybe it's still better for Peter to run and get him, because we need to know these distances first before we calculate it. Yeah, and then see what angle does Jonah look up at. So find me these things. Good morning. Okay, so I'll pause the video and then we'll talk about our solutions in just a moment. All right, so let's take a look at this problem, and we're going to see if there's two different situations that we can describe with it. I'm just going to take a stab at doing this in a more elegant way with fewer side bends. So there's two different possibilities here. Sorry, one moment. All right, so we're going to go through this problem a little bit more. So here, one thing that we can do is set this up with sine law, because we don't have any right angles. We'd like to know this angle, and we'd like to know this distance between them. Okay? We also might want to know how much closer is Jonah to the baby than Peter. So that we could use some right angle triangles, but in any case, here's how we can set these up. If we look at sine law, and we're trying to calculate for this unknown angle here, we'll call that angle J for Jonah. So this would be sine 34 degrees divided by the associated side, which is the opposite side to that angle, over 144, is equal to the sine of the unknown angle, sine J, divided by the associated side, 233. Solve this. We're going to multiply both sides by 233 to cancel these. We have to multiply it over here, of course. And that gives us this expression is equal to sine J. So then, let's just write that out. Sine J would be equal to 233 over 144 multiplied by sine 34 degrees. Okay? And then I'm going to take the inverse sine of both sides. So that J would be equal to the inverse sine inverse of 233 over 144 sine 34 degrees. This would be the exact expression I could punch on my calculator to find angle J. So when we do that, we found that angle J was 65 degrees. Trust me that if you punch that on your calculator, that's what you're going to get. But this tells us there's actually two different ways Jonah could be looking up. He could be looking up from this side of the spaceship, or he could be looking up from that side of the spaceship. In both cases, he would be looking up at 65 degrees. And this is an example of the ambiguous case of sine law. So it creates two different triangles, two different diagrams. So let's draw the other diagram in green so that we can do the math for it separately and then see how the maths are related. So this is still 233. This is still 34 degrees. And this is still Peter here. We simplify Peter to a very simple stick figure. That's Peter, P. And then here is Jonah looking up at 65 degrees. The distance from him to the spaceship is still 144, but now the 65 degrees is on the other side. Okay, so that would give us a different distance between the two of them. Okay, now the baby is over here. This is Jonah over here, J, and the baby would now be right below the spaceship, right about there. If Peter were to run to the baby in this situation, he would pass Jonah. In this situation, if Peter runs to the baby, he never gets to Jonah. Jonah's on the other side, still looking up at 65 degrees. And that actually explains the ambiguous case of the sine law pretty well. We can figure out that this here, we just continue this line, this is the ground, this 65 degrees, the ground's 180, so this would be 180 minus 65. So this would be 115 degrees. So now we have a triangle with an interior angle 34 degrees, 115 degrees, and that leaves us only 41 degrees up here. No, 31 degrees. This is a 31 degree angle up here. But in this case, when we do 34 plus 65, that's now known, that's 65 degrees in this diagram. This angle would then be 81 degrees. Okay, so that's going to create different expressions to calculate this x, or let's call this situation something different. Let's call that distance y. Okay, now let's work out x and y for these different things. But first, let's take a look at 165 and 115 degrees by thinking of them as angles in standard position. Here's my axis. Here is a 65 degree angle here. And that, if I reflect it over here, create this angle, well, that would be 65 degrees. And this would be 115. Both of these would have the same value of sine, because sine is the hypotenuse, which is the same for this angle and this angle, over the adjacent. The adjacent is the y value of these triangles. So if I draw a little triangle here, with the x-axis, that's the value of y. This value of y over here is still positive. It's the same. The value of the hypotenuse is the same. So that's telling us sine 65 is equal to sine 115. That's where the similarity is coming in. That's why we have these ambiguous cases with the sine law. It's because sine is positive here and sine is positive here because of Castro. C, A, all of them are positive here. Sine, cosine, tangent are all positive. And then over here, only sine is positive. So because these angles are both between 0 and 180, because they both occur in the first and second quadrants, they're both possible solutions to these triangles. That's why we have this ambiguity with the sine law. So now let's calculate this distance x up here, okay? So we're going to work on this triangle. So the distance between Peter and Jonah would be, well, 81 degrees is this angle. So I'm going to put my unknown on top, x over sine 81 is equal to, let's work with 233 and 65, is equal to 233 over sine 65. Multiply both by sine 181 gives you this. That's on top of the fraction, so I'm going to multiply this times this and divide by that, and that will give me x. And when we do that, we'll find that x is, I believe this was 254 meters. Okay, this is meters, that's meters. So you try that on your calculator. This times this divided by that should give you 254. Looking at that, that should be about a good guess. You know, it's going to be longer than 233. If I lean that down, it's going to be about there, and then it's a little bit more. Okay, and then I can go ahead and calculate down. Oops. Let's just do undo there. Okay, and then if I look at this one, well, here I expect something much shorter. Okay, so that is going to be defined by here. I'm going to have another pair of opposed angles, 233 over sine 115 is equal to, well, isn't sine 115 the same thing as sine 65 that we used up in this expression? Yeah, but we're not going to be using sine 81. We're going to be using sine 31 up there. So that's going to change our answer. Is equal to some unknown here, y, over sine 31. Because that's now our opposed angle here. It's different when we look at this triangle. So now multiply both sides by sine 31. And then we solve this, and that gives us y. And I'm just going to actually do that one and then let you know, because there was a little bit of confusion about that number. So this is an example of the expression that you would write in your calculator. Sine 31 multiplied by 233 divided by the sine of 115. Okay? And that gives us the answer 132.4. Yeah, so there we go. So that is the distance here of y. Y is 134. 132.4 meters. So in this case, there's 132.4 meters between Jonah and Peter. Up here, there was 254 meters. So let's expand this triangle. We'll draw both of them, and I'll show you how we can use that idea to solve their distance from the baby. So here is Peter. Here is our UFO. Here's Jonah in one parallel universe. He's down here. Peter, this is Jonah Prime, and this is a UFO up here. And this here is the tractor beam. There is the baby. Okay. Now, let's label our sides. 144, 233, and this length here was 252, 254. Can't remember. Up here, check it out. That was a 254. Okay, so that's 254 meters. But then there's another situation where Jonah is in a parallel universe. He's over here. Okay. And this distance was 132. Okay, so 132 and 254. 254 goes from here. Well, this is 132 from here to here. And 254 was here to here. So we can use that to find this distance. The thing with that is, this distance here is going to be the same as this distance there, because the baby is right in between where this pendulum is swinging. And so we can use that to calculate how far Jonah is from the baby and how far Peter is from the baby. So let's do that. If we had 254, subtract 132, and then I want to divide that in 2. Okay, why do I do that? This is 254 minus 132, and I have 2 even pieces on either side of the baby, where Jonah might be over here, or in the parallel universe, this is Jonah 2. That's the second Jonah over there. Okay, so that will give us the distance from Jonah to the baby. So let's calculate that. That would be 254 minus 132 gives us 82 over 84 over 2. Wait, what is that? 254, 132. Did I write these numbers down right? Yes, I did. Okay. Yeah, that's good. Yes, that's good. Yes, so that's 122 over 2. That's equal to 61. 61 meters. So that answers the question, how far is it from Jonah to the baby? 61 meters. We could also have used one of these triangles to solve that. Okay. These are right angle SOHCAHTOA triangles. This is a known side. This is a known angle, 65 degrees. We found that out by calculating. This one also 65 degrees looking up with the same side length, 144. So it will be the same solution to that problem. So that looks like this. Cosine of 65 degrees is equal to the hypotenuse over the adjacent side. That's why I chose cosine, because it relates this side here, which is d, distance from Jonah to the baby, okay, is going to be equal to d divided by 144, divided by the hypotenuse. Multiply both sides by 144 so that that cancels. And then I have, this is times 144. And this gives me what I punch on the calculator, 144 cosine of 65 degrees equals d. Okay, that's what I punch on the calculator. So give that a try, see what you get. And you will get, let's take a look. Here we go. So I'm just going to clear this, 65 degrees, and I'm doing cosine of that. And then I'm going to multiply this by 144 equals, isn't trigonometry beautiful when it all just works out and it all matches up? So that's how we can take apart this type of problem and calculate it in a variety of ways. So it just reinforces that we get the same value. The D for the distance to the baby, oops, that's a B, Mr. Jennings. D was equal to 61 meters there by SOHCAHTOA. It was also equal to that when we used this interesting feature of the ambiguous case of the sine law. So I hope that leads you to some fruitful practice. Your textbook questions today are in the D2L. You will see them here, page 256. Numbers 1 to 5, 7, 8, 10, 12, 18, and 20 are the questions for today. Contact me with any questions you might have.